All right, I think we'll go ahead and get started. Welcome everyone to week 2 of our distinguished lecture series. A reminder next week that we have Kathy Weathers from the Carey Institute in the US. She'll be talking about catchment river and lake biogeochemistry. And as always, I want to thank the Global Institute for Water Security and Global Water Futures for underwriting this seminar series. And today I've asked Saman Razavi if he would mind coming and introducing today's speaker. So, Saman.
Thank you very much, Jeff. It is actually a great pleasure and excitement to be part of this distinguished lecture series again this year. And this is our great pleasure to have Ximing Cai with us here in Saskatoon. Ximing is Colonel Harry F. and Frankie M. Lowell endowed professor in civil engineering at the University of Illinois Urbana-Champaign. He received PhD in 1999 from University of Texas at Austin, and then spent some years at the International Food Policy Research Institute in Washington, D.C. as a researcher before joining faculty at the University of Illinois in 2002, since he has been on faculty since then. Ximing is a thought leader in the area of water management, hydroeconomic modeling, and coupled human-natural systems. He has published over 130 papers in peer-reviewed journals and multiple books in this area. I remember reading his papers and basically PhD thesis in my very first days as a researcher when I just was a fresh master's student in Iran, probably back in 2002 or so. So he has significantly contributed to the area over the years, and so I'm a big fan of his research in that area. And now having him here is actually very timely as we are ramping up our research on integrated modeling of natural and human-driven systems under the framework of global water futures. So he has already generously provided us with a lot of input to the program, and many of us have had very fruitful conversation during his visit, basically since last night. For his outstanding work, he has received several awards, including the National Science Foundation Career Award and Best Paper Awards from 2 prominent journals, Water International and the ASCE Journal of Water Resources Planning and Management. He's also on the editorial board of several journals, and currently he's the editor of WRR, the basically top journal in our field, water resources research. So it is a real pleasure to having Ximing with us today. Please join me in giving him a warm welcome.
All right, thank you. All right, thank you, Simon. Thanks, Professor Jeff McDonald, for inviting me to give this talk. It's really my honor. And thanks, everyone, for coming to this talk in the late afternoon. Okay, so I believe some of you have already studied this diagram. This actually is a cartoon post of the so-called first distributed watershed model. It's also called a Stanford model, right? As you can see over there, this is a post for a hydrological model, but it has a quite complex human dimension and even has some ecological dimension. All right, so before I talk, let me tell a little bit what my place looks like. All right, so I came from University of Illinois. So in the center campus, there is a cornfield, and this is actually the first experimental field for corn in the United States. And I'm not sure if you read Professor Winter Child's book on applied hydrology or applied handbook of applied hydrology. You might remember the name is called Boneyard Creek, right? Because a lot of examples, even homework problems, they're designed based on this little creek. And we still have a little prairie land, very beautiful prairie land, but the majority is a cornfield. And so it's so easy in the summer, it's so easy to get lost in the cornfield if you are not familiar with the region. Let me show you the kind of share with you water view of our region. So in late spring, we often say some ponds or lakes in the field of cornfield. That's kind of flooding, and the crop will be seriously damaged. So that's why we need a very heavy drainage. So without drainage, so basically the land will be wetlands. So it's not possible for agricultural purpose. So this one shows the drainage channels in around Urbana-Champaign. There was a joke. They said someone found a job in Urbana-Champaign, and then he wants to know what the place looks like. And then he used Google Earth, and he found most of the streams in this place run out of the region. He said, "Oh, that place must be in a top of a mountain." And then of course, when he came to the town, he got very disappointed. He said, "Why this place is so flat?" Because most of the streams are drainage channels. Okay, that's a very distinguished human dimension of the water system in Midwest, and especially in central Illinois. So that also shows a kind of tile drainage. So we build the pipes underground and it drains the land. And this drainage actually has been claimed as the major reason for the hypoxia, for the nutrition problem in Mexico Gulf. And it also represents very strong political entities in Midwest because the farmers need that. They need drainage. Without drainage, agriculture will be very much affected. But we also know environmental has been affected with that. So probably some of you have looked at this figure, right? This just shows in high plains. So they pump groundwater for irrigation, and there is like a sprinkler, which is a sprinkler of several hundreds long, and they just pump the water, distribute the water around the central point, and you see some landscape reflection over there. Oops. Sorry. Okay, so. Last picture, I got this picture from China. So this compares the lowest plateau in northwestern China, Laonan Dam. And so some years ago, before the very extensive, before the soil and land conservation, the landscape looks like this. But this is what, in many places in North Plateau, you will see something like that. Very intensive soil and land conservation. So we can imagine how hydrology or geomorphology has been changed in those places. All right, so today, first I'm going to share with you some of my observation about the hydrology and water resource management. My kind of view is that those two areas used to be split very deeply, and now they are moving toward a common path. And then I will share a little more about my own research. That's how to identify the human footprints in hydrological processes. And finally, I will talk a little more about my own perspective about future research. So let's start to look at this chronology of water governance in the US. It started from navigation and also the land development by European immigrants. And then then there was all kinds of engineering, irrigation, drinking water supply, power generation, flooding control, and up to after Second World War, recreation became important. Okay, and then around 1980s, restoration became a major issue. I just remember U.S. Army Corps of Engineers. They just had to totally change their function because before that, the major function is construction, engineering construction. And after 1980s, they have to focus a more on small, relatively distributed and small-scale restoration. And then starting from 1990, we got this bigger word. Right? We got this bigger word, sustainability. All right, so I try to put the trajectory of hydrology together with this the governance concerns. So we would say hydrology originated from fluid mechanics or geographical hydrology, and then around the time, there were basically two branches. One branch is more on applied hydrology. So we have engineering hydrology, and then when the pollution became a major issue, there was a kind of branch on environmental hydrology, and then eco hydrology serves the restoration. Okay, and the other branch is more on geoscience. Right? We treat hydrology as a branch of geoscience, and we got a little joint work with eco hydrology. And then the question is, what is the next? Okay, what is the next? We may not need anything, okay, but there's some voice. There's some strong voice from community of hydrology, social hydrology. So my colleague, Professor Sivapalan, he was here a few years ago. I believe he talked about that, social hydrology. So the idea is that we now, in order to model and predict hydrologic processes, we have to account the social part. And then another colleague, my friend Richard Vogel, he was here too. So he talked about hydrogeomorphology. So his point is we have to understand the human footprint first before we move to the so-called social hydrology or any other. So anyway, there are a lot of big ideas. So now let's shift a little bit to the community of water resources systems analysis or water resource management. So normally, many people would start the modern water resource management in the United States with a Harvard water program. So that is in around the end of 1950s. The Pakistan government requested U.S. State of Department to help them on river-based management. And then the state government, they gave this task to Harvard. Harvard said, no, actually in the US, we don't have a river basin authority. And we did not do much on river basin management. And then several professors from political science, from social science, they said, why not we figure out something? Okay, so that studied the idea of Harvard Water Program, but over years, it indeed contributed a lot. It studied the interdisciplinary studies, and it brought the computer simulation around the optimization models, simulation models into water resource management, and also like wide application. It has been really applied to many real-world river-based management problems. Okay, but starting from especially in the 1990s, early 1990s, Harvard program was criticized. And the criticism was more and more intense during that 10 years. And I found these two very interesting statements. One is given by Professor Thomas Fearon. He's one of the prominent Harvard Water Program participants. He said the question is whether one would rather be right or be president. So as a scientist, I would rather be right. But as an engineer concerned with water resources planning, I would rather be president. Okay? And then later on, after a lot of criticism, in 2003, a US SAE historian, hydrology or water resource historian, he wrote a very interesting paper. And in that paper, he said, Harvard colleagues spend less time looking at the exact right model, and more time trying to provide reasonable answers to both political and economic questions. So he really meant the Harvard colleagues, have been president more like a right scientist. Okay, and then he suggested it's the right time in 2003. It's the right time for us to resurrect the Harvard Water Program with a large focus on science. Okay, then for water resources management in the U.S. and probably around the world, what kind of outstanding science issues? In other words, what kind of gaps we had before and we might still have it today. The first is that we have done a lot of investments. So we could predict the short-term impact, but we often missed the long-term impact. Right? And that has caused a lot of environmental problems, a lot of even social problems. I have some examples later on. The other one is that So we talk about water allocation, right? Because basically around the world, in many places, water has been fully allocated. But what is the behavior economics and the political science? What is the science basis beyond the water allocation? So in other words, how is the water allocated based on science? And then another issue is that how could we predict the environmental response to water use? That's, of course, I mean, when we talk about sustainability, that's a major issue because our environment has been affected a lot by human water uses. And then how could we, I mean, at a large scale and also at a long-term time scale, how could we understand the feedback from water uses on hydrology, on local hydrology, and also hydroformology? So a lot of systems models have been developed, okay? But there are few models which could repeat what happened in the real world. So people argue, say, all right, the reason for us to do optimization model or kind of simulation model is that we want to find out better solution. But why not you first show your model could really simulate what happened in the real world. Few people could do that, okay? Because we often missed something. So, and the other one is the water demand. So in 1970s, there was a prediction on water use in the world. And it said, compared to 1970s, up to 2000, the world water use will be tripled. But it did not happen, okay? It did not happen. There are a lot of issues beyond science, right? There was some human adaptation, human behavior issues over there. What is needed to be right for water resource planning and management? So in one of the papers, we summarize that in these three aspects. So first of all, we want to find out some evidence of scientific validates of the models we used. So after we describe the model, how could we validate the model from a science perspective? One of my colleagues, he's Praveen Kumar, he said, I never use calibration because calibration is like you try to make the model right by yourself. I usually validate my model. But for people in water resource planning and management, it's very difficult. It's difficult for us to find out some scientific evidence for the. And the other one is how could we provide the scientific explanations about what we found? So we usually get very much better solution, optimized solution. But how could we explain that from a science perspective? That is limited. And for the feature prediction, feature modeling, what is the basis, okay, scientific basis. All right, so now I organize what is happening now by this diagram, by this figure. So hydrology is moving to somewhere, and water resource management is also moving to somewhere. And we might be able to use a common term to integrate both. I call that as action science, and in some places they call it as the user-inspired science. And this science has been motivated, this development has been motivated by sustainability, right? To solve the real-world sustainability problems. And also we really, because when we got human dimension together with the natural dimension, the systems becomes very complex. So what kind of new knowledge could we find out? So, and then when we try to predict something, so both the human and the nature systems should be the joint predictor in order to get things right. Okay, so let me share with you the development of water resources research, and I try to use that to support what I just claimed. Okay, so this is a kind of cover page of water resources research at a different time, and a few years ago we published we did some kind of word mining using the keywords with the abstracts and the keywords, and this is what we found every 10 years. So we divided 50 years into 5 10 years period. So you can. So, by the way, WR started with an interdisciplinary journal. So in the very beginning, we had an editor from from physical science, from hydrology. We also have we had an editor from economics, and that has been continued until 1990s. Okay, so you can based on this the size of these words, you can say the focus of different time period, right? And it's particularly I particularly want you to look at the size of water, right? Because water really water represents a more broader, right? A broader context than hydrology or hydrologic work. So it starts with a large size, and then it got small, got bigger again, and recently it got bigger. But for some reason, we just put it upside down. Okay, that's not for purpose. Okay, but what happened? What happened to this time? What happened? So during that period, this is the time we call the water management is dying in the U.S. There was even an article about that. So during that period, only a few people from Citizens era could publish the papers in WRR. As I mentioned, in 2015 or 2016, we published a 5th year anniversary special issue, and this we put papers. It's almost like about 57 papers. We put these papers into different categories. And when we found these numbers, even all editors, we were very surprised. Because we invited a lot of papers. Of course, we invited some papers from legacy of hydrology. From a historical perspective, we show how science moved forward. And the majority of the papers invited are from water processes, fundamental processes. I invited 5 papers on the last category. But eventually, many people, okay, they have very good name in fundamental processes. Their paper is about a water issue, a water strategy issue. So of course, we accept those papers and publish that. So that basically shows people's concern. I would say because of the sustainability, because of the recent environmental issues, the social concern has been shifted, and that has affected researchers in water. Okay, and I also like to share with you a perspective from late Professor Winter Chow. He was the founder of our laboratory in University of Illinois. I found this figure from our proceeding, the conference proceeding in 1971. It was, and he tried to put how to solve real-world problems. How could we put different areas together? And it's very interesting. He put hydrology and economics together because I believe he realized we both do quantitative models, right? So both economics and hydrology, we do quantitative models. But he also realized we still need some other areas. They don't do much quantitative modeling, quantitative work, but we still need them. And he also recognized, even that time, he recognized this model, the optimization, right? We always want to find the optimal solution. Optimization is not like a linear thing. It's not straightforward. And it often means repeating and self-adjusting. So this is consistent with the concept we talked today, right? Adaptation. So I like to add one line just to say after decision making, what happened in the real world will eventually affect everything there. Okay, will eventually affect hydrology, economics, and many other things. So that is probably what today we really want to put some attention. How could we quantify that feedback? Okay, so now I move to the second part. I'm going to share with you some results from my own group, and we try to look at to what extent why we need to care about the human impact in hydrological processes, and to what extent the impact is. The first thing I argue is that the human impacts are not linear. So in a lot of modeling, we focus on physical processes, and then we just add or subtract water uses. So the assumption beyond that is the water use impact is linear, but actually it's not. It's very, very big nonlinearity. I'm going to give an example. The other one is the human data errors. So when we try to calibrate a model for management purpose, right, we have to calibrate the model and make the model results fit some historical records. So if for the cases with a lot of human inputs, like water withdrawal, groundwater pumping, what we usually do is that some cases, we just ignore that. We say, all right, that part is small, we ignore that. Or we say, they are fixed. I have perfect data for the human water use. Both are wrong. Usually, we really don't have, for large-scale modeling, we don't have perfect data. And that was recognized in a white paper published by the National Research Council of US in 2000. The data is the human water use data is a big issue. So if the human input data are wrong, and we take the right, and then we calibrate other parameters, that means we some way convert the error from one part to the other part. Okay. And also, finally, I'm going to show a lot of many empirical hydrological relationships. They are widely recognized, but with heavy human interference, those relationships may not hold, may not be right. Okay, I will give you some examples. So this is a typical case for nonlinearity. Okay, for the nonlinearity this is our say in Central Asia. And the black line here, it shows the development. Sorry, I'm not sure this works. Oops. So in this one, we have the black line shows the increase of irrigated area, and the below line shows the inflow to the lake, to the ROC. And then we also have the surface of the lake. What happened around 1970? So before that, we have regular fluctuations, and that's kind of expected, right, by people. But right after that, we got a threshold, like a tipping point. After that, the inflow and also the surface of the lake never went back. And then some people ask, if irrigation was slowed down a little bit or was stopped, what will happen over there? We don't know. It looks like there was some cumulative impact even before 1960s. All right. So that's a case of nonlinearity. Okay, and then as I mentioned, for management purpose or for engineering design purpose, once we get a model, we have to calibrate that before we use that, right? So here we have a case that we try to simulate a watershed response, okay, but at the outlet of the watershed, there was a dam, okay, and there was a door with the dam, but we did not have a record of how the door was operated, like when it was closed, when it was opened. We don't have that data. Then my colleagues said, oh, we ignore that, right? We ignore that. And then they calibrate the model, and what they find, they found some solutions. They get some good match with historical data, but the parameters, a lot of parameters involved in the model, they are not physically meaningful. So then what we do is that we don't know the release from the reservoir through the door. Why not we assume there is an aerotem over there? And we try to understand the pattern of the aerotem. So in doing this, actually, we don't find like a perfect solution, but we found some reasonable solution. So extended from this idea, we got a grant from US NSF. We got economists to help us to understand how pumping data, the error with the pumping data is distributed. Or in other words, from an economic perspective, how is the pumping data probability distributed? And we incorporate that into the model flow calibration, and we got some interesting results. Right? So that's an example. And this figure shows we did some analysis on the recession slope curve. And Professor Brozard at Cornell, So that's probably in 1970s, he published some very important paper on recession slope. And one of his basic findings is that with natural watersheds, so if we plot these two terms, right, the time rate of the flow and the average flow over years, and then you will get a log linear relationship. And the straight line provides a lower bound of the data points. That's what he found. And then we follow what he did. We just plot the line and the data points during different time periods. And as you can see that, over time, the points are moving up or down. And then in recent period, we can see all the points moved down. And this lower envelope becomes an upper envelope. And it is not linear again, right? We should not use it. It's a nonlinear relationship. And this one just shows this is an example, as I want to say, a lot of the important findings without considering human impacts, and they may not hold today because of the impact of human activities. And this one also shows a relationship between the ET and the potential ET normalized by precipitation. There are a lot of work, a lot of publication. They showed a curve. This should follow a curve. We usually call it, sometimes we call this as a particle curve, although this does not exactly follow the concept of particle curve. But many people showed a curve, right? But we got many data from many watersheds, about 400 watersheds in the United States, and we plotted the data points. And in the watersheds with irrigation impact, with larger land development, the curve is more like a straight line rather than like a nonlinear curve. So we some way, as we showed, the more development, the linear relationship is stronger. So we attribute this to the impact of human activities then. So the last case I'm going to show, so this actually we did some project in Republican River Basin. We try to understand the inter-year variability of evapotranspiration. So in the Republican River Basin, I believe some of you have heard about that. This is one of the basins in the United States with very heavy irrigation development. And then so the river flows from Colorado and then going through Nebraska, the most important agriculture state in the United States, and then down to Kansas. And around middle of 1980s, Kansas sued Nebraska and Colorado. They said, you depleted my water because the flow to Kansas becomes very low. And then actually they sued that through the Supreme Court of the United States. And then after a few years, Nebraska fight back. Nebraska fought back because they got to know the people from Kansas. They use a lot of data from model flow. They use model flow, the modern results to support their arguments. They say how, and we can show the relationship between irrigation development and the stream to Kansas. And then Nebraska people organized a team of groundwater experts. And they found actually the model flow, they said, Kansas is not right because this model is not exactly right. Why? Because there is a lot of return flow from the land. And the model flow does not consider about that in a meaningful way. Then they told Kansas people that you cannot use this model as evidence against us. So that's a kind of story about if the human dimension is missed, then the model may not be realistic. Okay? So as I mentioned, so this figure just shows the number of wells over time, and you can also say the average flow in early time and in recent time. So in recent time, it becomes really low. Right? And it's interesting. So we plot the potential ET and actual ET precipitation and then runoff. And we expect to say some, just like naturally, in wet years with high rainfall, we would expect high runoff, right? But we did not say that. We don't say the high, so we don't say the kind of expected response. The reason is really in wet years, although the ET might be potential ET, the ET could be smaller, the rainfall could be higher, but a large amount of water is recharged to the groundwater because the groundwater is depleted. Okay, so that's kind of explanation about the issues over there. And we also found the irrigation and the return flow totally changed the groundwater recharge and discharge pattern. So in the beginning, this is what we say. So basically, in the summer, we have recharge, and then in the winter, there was some discharge, okay? Because in the summer, we got rainfall. So over years, this pattern is totally changed. And now, basically, in the just opposite. In the summer, we have some discharge, and then in the winter, we have recharge. So that's also this. I mean, it's due to the return flow from irrigation and the pumping practice and return from irrigation. And then we first look at how ET variability is affected by irrigation activities. And in this figure, you can say that this is one of the watersheds in the high plain area. So ET increases a lot, basically, in many regions because of the irrigation. And by average, ET increase, almost more than half of the ET increase is due to irrigation, okay, compared to the natural precipitation. Okay, and then we first look at the inter-year variability. And we also found before the development, before the very intensive irrigation, and after that, there is a very different pattern of inter-year variability of ET. So then we try to figure out how much. So how much impact is caused by groundwater storage, pumping and groundwater storage change. And so this equation, actually, we started from this equation. So this equation is from Kosto's group and described how ET inter-year variability is related to precipitation. And we extended that equation. We account the correlation between energy and water. And we also consider about the storage change, the terrestrial storage change, and the contribution from the storage change, and also the correlation between the storage change and water and energy. So, so based on this equation, we figure out actually a large fraction of ET change. Sorry. I hope I can continue. Okay, and then we plot the data, the coefficient of variance, and the mean ET before and after development. And we see some pattern here. Right? So before the development, so basically we have relatively low average with high variability. Right? And after the development, after the impact of irrigation, we have another pattern which are shown by the red points. So here we have relatively high mean and relatively lower variability. Okay, and then in this figure, we try to compare the crop yield, with the ET variability. So we found some correspondence, right? So for the crop yield, we plot the rainfall yield and irrigated yield. We can say basically ET and the crop yield, they follow very similar statistical pattern. We might be able to use like a power law relationship to describe both patterns here. Okay, so this is a I hope I have enough time. So this is I want to share with you some research from my group. We try to understand and quantify the human impacts. And the last part I want to share with you a little about my thoughts about the future research. It doesn't really mean all hydrologists or all water management analysis working this way, but I just hope maybe some people should follow this way, okay? The first, we emphasize a lot about systems approach, and actually this has been reflected about the recent call for proposals by US National Science Foundation, and one of the is called coupled human nature systems. So U.S. National Science Fund, NSF, has been supporting this program over 12 years. Right? A lot of hydrologists, water people, we got grants on this. So basically, we want to understand the coupling of the dynamics of the hydrologic dynamics and the human dynamics. So let me just show some very general approach. Okay, we really have not done much. So basically, we could not say the inflow is not equal to outflow, right? If we just ignore the storage change. But we, in the real world, both inflows and outflows are very much affected by the human activities. So how could we incorporate that into the mass balance equation? So the same for energy, right? We should have the energy conservation, but a lot of energy, a lot of additional energy is inserted by human activities to the water systems, right? Like when we're pumping groundwater, we have to use energy artificially. It's not just like everything is controlled by the gravity. So, and then in terms of the systems dynamics, what are the driving forces? Okay, what are the driving forces for energy and water flow? So some people joke about that. They say today a lot of water flows up to the mountain. It's not like naturally water flows down, right? And they say, all right, so maybe one of the driving forces is the marginal value of water. Water is driven by money. So regarding from the systems equilibrium perspective, what we really want to understand is the co-evolution. So if we look at the historical data for the two systems, so we try to find out the covariance or some kind of co-relationship between the two. And also, a lot of people are talking about resilience. So here we use a concept from ecologists. So ecologists they measure the resilience of the system as the amount of disturbance required to push the system from one basin to another one. Okay. So basically here we just shows how water quality in this part, the upper one shows how water quality is changing in a lake. And then this circle just shows the kind of development and then restoration, that kind of human cycle over time. So at some point, the system equilibrium has to be shifted to another state. All right. So, but if the system could not shift, then that basically means we would say the resilience, right? The system is not resilient enough. So this concept has been used a lot. So about systems approach, recently the field nexus, the food energy nexus has been emphasized a lot. I'm not sure if Canada has put in money on that, but in US, there is a lot of research funding. That becomes a major research funding sources for hydrologists and for water systems analysis. So field nexus, sometimes we say it might be explained like almost no nexus. So in the past several years, there are about 800 papers about that in all kinds of journals. But if you read like half of them, you will realize nobody is really talking about nexus, almost no nexus. Then if we add, a lot of people, they add environment to the end, right? So if we do that, then that becomes water phase. That's the way economists like very much. Maybe economists say if we can put everything into the money, done. No complexity. Right? That's kind of a joke anyway. So, but to my personal understanding is this nexus really means three things. The first, water, energy, and food. They are all resources. Right? They are resources. There is some input-output relationship. And one of them could be an input to another. Right? So that's a relationship. And the other one, it really means a lot of collected fundamental processes So for example, even the ET, right? We hydrologists have studied ET a lot, but today it still remains kind of concerns on how ET and the crop growth and the biomass, there is still a lot of research issues over there. If this fundamental problem is not solved, at the systems level, we will not be able to do much. Another case is the water quality response to agricultural development. And this is a big problem in US Midwest. So, and the other thing, if we treat fish, aquatic, if we treat fish as a part of the food, then what is the relationship between hydrology and fish? That has not been touched much. Anyway, there are a lot of fundamental issues which could provide opportunities not only for systems analysis but also for hydrologists or processes-based hydrologists. And from engineering and the institutional perspective, the issue here is that we could find a lot of overlaid institutions and infrastructures and also markets. So because of the overlay, there might be some inefficiency, or there could be some opportunity to improve the efficiency for the whole system. Okay. So that's actually recently we wrote a review paper. We try to address what does this field nexus mean to water people. And we could not say much on behalf of food or energy people, but from a water perspective, what kind of new opportunities we could have, what kind of challenges we have. All right. So another thing I really want to emphasize is the data side, on the data side. So today we might say we may not have, several years ago we worked a lot on POP, right, on this prediction of ungauged basins, but those basins are, I believe the number of those basins are declining because of the sensors and the global data access. There are a lot of global data sets which could be used even for basins in some very poor countries. So there is already a debating about data-driven model versus physically based model. Especially with the increased computing power, based on a large amount of data, we might be able to find out something based on the data-driven models. And a lot of relationships, as I just mentioned, if we have the human water use data, and a lot of empirical relationships could be updated, or we might be able to find out some new. So the difficult for us to consider about the human hydrologic, the human component of water system is we really don't know much about, we don't have much data. Traditionally, we don't have much data on the interactions of these two parts. And especially like return flow, as I just mentioned, or human-induced surface groundwater interactions. And those areas, they have not really made much progress because of the limitation because of the data. And now with the so-called big data, there might be some hope. Okay. And finally, how could we quantify human behavior? Because when we talk about human dimension, behavior and sometimes institutions are very important. So based on the social media, there might be some opportunity to describe or to quantify those components. And then, of course, finally, we have to work with social scientists. I believe we should have some social scientists in this room. I have been working with economists for many years. I have a lot of economic friends. But I also met some cases that economists, they don't want to work, they even don't want to talk to me. They said, you are even use some wrong terms. So yeah, I just remember when I first used, I said water demand. He said, how much do you understand about water demand? I said, all right, sorry, I have to change water demand to water requirement. That's a physical term, right? So and also you recent papers on social hydrology or other human interference, you can say the authors might use sensitivity or sensitivity to the society or sensitivity to the environment. And then some social scientists might say no, and we already defined that. It's marginal value. So I just, it's not, we really have to work together to define some compounding or intercollecting variables, and hopefully we could sit together to write some differential equations, and then we might be able to do some analysis if data are available, okay? But for the human side, I used to talk to Professor Peter Laux. He said, don't try to promote that because you will not have data. Just stay with optimization. So, but today I'm more confident because of, we are really on the human behavior side, we are getting a lot of data sources from social media, right? So I have a student right now, he's developing a tool to extract some information from social media about the flooding evacuation in Houston. We have not got the results yet, but I hope that will be really interesting. Okay, so, and then of course, why do we need to do that? As I mentioned in the very beginning, there are a lot of compounding, a lot of pressing issues. Many places we have growing human interference. So for example, like Yellow River in China, basically it's a human controlled, it's fully human controlled river. It's not a natural river anymore. Anyway, I believe there are many places, many rivers like that and also for sustainability purpose, we are talking more about returning some water back to natural systems. Right. So how beyond the institutional difficulty, from a science perspective, how much water is really needed for the environment. And then the role of engineering. What is the role of engineering? So usually with engineers, a lot of places engineers are criticized. So in the U.S. for flooding control, the father of U.S. flooding control policy, Professor Gilbert White, he said, flooding is basically an act of God, but flooding control is largely an action of human. So he said, the more engineering, the more damage. That's his statement. So you see, there's a lot of debate about how as an engineer, as an engineer in training, I believe we of course we need engineering, but how? But how could we do better? There is a lot of issues. Stationary or non-stationary, that's a big debate in hydrology. But if we convert that into water resource management, then that's we manage mean versus managing variability. Traditionally we manage mean, but now we need to move to variability and also the adaptive management. Water reallocation, I discussed a lot with Jeff's class. Anyway, that's really it's a kind of urgent issue, but it's very difficult. In many cases, even beyond both natural science and social science. And then when we talk about water scarcity, I think for many cases, so the real issue is with the social equity and the underrepresented group. So that's like in California, during the big drought in California a few years ago. They said they have to they put larger constraint for rich communities and the lower constraint on poor communities. And eventually they found there's no reduction in the from the rich community at all. The water use remains basically the same during the drought period. So a lot of things which could cause our attention. All right, so what do we do? Where do we go? Again, I don't really mean everyone should go to one direction, right? But recently, my colleague, Professor Siva Palan, he wrote a paper with Ganto Blosho. It's a perspective paper. They try to review the path of hydrological development. They say we should collect the dots along the social needs and the technology development. And they also say the whole process of hydrological development is a cycle of euphoria and disenhancement. So at some point we have euphoria, we got very excited, and sometimes we got very disappointed. I hope right now we are at the stage of excitement. All right. So, but maybe after a few years, people will say, let's go back. Let's just go back to fundamental process, and let's not talk too much about this systems issue. Okay. So I use this graph. This is my last slide. All right. So and this is the Danube River, and then because of the upstream down many European countries, they depend on this river. There were also water quality problems, and they organized a commission, right, with a representative from different countries. And I think these guys are a little interesting because they really should put each of them got the part of their own country, right? They should really put this together as a natural map, but they did not. Okay, so I think what we really need for effective water resource management is we want the model. If we talk about a model, right, we need a kind of scientifically sound, right? We really should get more science involved, embedded in your work, and then it should be institutionally realistic, okay? Because a lot of that's basically on the human side, and of course computationally should be tractable. And that's also actually that provides that's in recent years, US and NSF has put a lot of emphasis on that. Got computer science involved with some other programs, and then hopefully we would have a new generation of watershed models. Okay, thank you.
Thanks very much, Ximing. We have some time for questions.
Sorry, I did not control the time well.
Okay, there is one back there. Could you take them?
Okay, yes.
Thank you, Ximing. Very interesting talk. I think most hydrologists are stuck with the concept of watershed. This is where we can do our hydrology, especially hydrologic modeling. But when you talk about things like water, food, energy nexus, you cannot do that at a watershed scale. You have to do it on administrative boundaries, a province or the country. But on administrative boundaries, you cannot do the hydrology. Because there's no watershed.
Yeah.
So again, the problem of all models is that we have to truncate it somewhere. It's either spatially or temporally.
Yeah.
So how can we really marry those two concepts here?
Yeah, that's indeed an issue. But I think many people still propose to use watershed because among the three, water, energy, food, only water has a natural component. Right? The food and the energy, obviously there are many controlled by, they could be controlled by human. So I kind of agree with that, but of course, it's not necessary. A lot of nexus, a lot of interactions between those things, they could happen at local scale, right? They could even happen at even a larger, like a regional scale, if we consider about the trade. Right, the trade of energy trade or food trade.
Ask a follow-up question. So you gave the example of Oral Sea, and you said there might have been a tipping point that basically pushed the system to an alternative equilibrium system, and you showed some examples from ecohydrology on that. I wonder what's your take on where we are now with the current generation of models? Do you see in near future we can have a model to be able to understand the upcoming tipping points, for example, to mitigate, for example, or change the direction of trajectory, for example, to the future?
That's my dream, to be honest. That's my dream. I don't really have, I tried some analytical model, my group, but was not that successful. But anyway, I'm not sure anyone in the world could simulate that occurrence. Unfortunately, I'm sorry. I don't really mean we will have a model very soon to simulate that. It's very complex, I believe. Right?
Yeah.
Yeah. So there is. All right. Yeah.
I guess one issue is, last week we had Bill Dietrich here, and he was showing some of the fundamental gaps in knowledge of how transpiration works, how groundwater recharge works based on process studies. And to model that, you need a very complex and sophisticated model, it seems, because the less we know, the more highly parameterized it seems the model needs to be to work. But then when we go to coupled human systems like you're describing, and we try to get at maybe the interactions with the various pieces of the system, it forces us to use ultra simple models to ultimately pull it all together, because computationally to bring complex models all together is not possible. So I guess I'm wondering what's the way forward, or if you agree with that kind of. current state I've described?
I mean, from analytical, we still like including Sewa and many other social hydrology researchers. We hope we could develop some analytical model, relatively simple model, to show the impact, to show how the human will affect will interact with the physical processes. But to be very honest, I have not seen many successful kind of good publications on that side. On the other hand, for numerical modeling, that we have done a lot. We coupled some like a human dimension model with a physical model. We could kind of mimic the history, and we can also identify some patterns. So of course, computationally, that as you said, that really brings up some computational issue. But that's probably like what we said. There is no free lunch, right? When we want to consider a little more, we always have to get some help. So I mean personally, I really hope this. Like cloud computing, high performance computing will provide us better chances to for the numerical modeling, and hopefully that we might be able to dig out some fundamental principles from the modeling exercise.
There's a question here, and then Graham.
Yeah, it was very interesting talk. Thank
you.
I have kind of two questions. The first one is like follow up on Jeff's. I mean, do you think we need to move kind of from microsystem perspective to macro system? I mean, it has been previously done, for example, in thermodynamics. People couldn't understand the particles' behavior, and then they build a macro kind of system, and they move forward. So do you think that kind of shift is necessary in hydrological modeling? And the second question is, we had a kind of experiment with someone that kind of small coupled model which had hydrology and economy. When you add stochasticity in the model, the behavior is totally changed. You may see a regime shift in the system. And we know, so economy and human behavior can maybe modeled by this kind of stochastic behavior. So you talk about nonlinearity and complex behavior. So I was just want to know your perspective on this adding stochasticity and models.
Okay.
Yeah.
I mean, for your first question, I don't think we should anyway scale up. I don't really mean like local scale hydrological work is not useful. It's very useful, and there are also local scale management issues, right? So particularly for some the biomass for crop growth. But for many water management issues, they are at the regional level, or even at the basin level, or even now people are talking about a virtual water flow. They are at the global level. So then, how could we scale up the small scale work to the basin level and even to the regional level? So back to 1990, when I worked with IFPRI, I couple a water model with a food model. That basically is a partial equilibrium model on food production, demand, and trade. So around that time, there was only one group. They could claim they had a global hydrological model. That is water gap, and it was criticized by so many people. But that's not the case today. So today, I think one of the big progress in hydrology is that now we have many people could claim their group has generated a global model. There was even like a review paper talking about that because of the data. I mean, the global data assessment, like Eric Wood's group, Dennis Nattimer's group, they already extended their model to the global scale. So the second question is, of course, it's not easy to couple those things. As I said, we do have to learn from economists, right? So from social scientists. But in my group, what we are doing now is from a technology perspective, several students, they are working on agent-based modeling, and we work with some social scientists. So how could we how could we represent human behavior rather than just use a single objective like optimization. So on the other hand, also I have a student. He's using data mining approach to extract some even some bounded irrationality. Bounded irrationality. That means people don't always perform rationally, right? So how could we catch that? Data, some of the data could tell us. So as I said, it's a research issue at this moment.
Yeah, I'm a bit mindful of time. Grab, could you, a quick question, yeah.
Oh, I don't know if this is quick.
Go ahead.
Okay. So you
Maybe I'll
sound
just make a quick comment, and that's that it's really exciting, the idea of using social media to help inform the modeling side, but with great caution in the sense that social media is people represent themselves on social media the way they want others to see them.
Yeah.
So it's not necessarily a good representation of how they actually behave.
Exactly.
And that's so with great caution. I think if the same level of rigor is applied to that as is to developing the hydrological models in the first place, I think we'll be in good shape.
Yeah.
Yeah.
I fully agree. But we just published a paper to show how social media affect flood evacuation. Although it's based on a hypothetical model, but we did show the negative impact of stubborn agents. So there were some stubborn agents that they don't believe anything, but they affect labors. So we did some analysis on that.
Stubborn agents think they're called Republicans in U.S.
Okay.
On that note, I think we'll bring this seminar to an end. We're all going to make a wander over to Boffin's for those that might want to join and continue the discussion. And thank you again for visiting us here in Saskatoon.
All right. Thank you. All right.